Okay, so first thing we're going to look at is some proofs that we've delayed until now. And the main reason we delayed these proofs was we wanted to have some additional notation, some syntax, some ideas from chapter 5 that we can, or chapters 4 and 5 that we can use to make these proofs a little more, a little easier to write down. The first theorem that we're going to discuss is Chebysheff's theorem. And the assumption is that mu and sigma are finite numbers, and the k is a positive number. And what Chebysheff says is that the proportion of data points, remember, we're thinking back to like chapter 3 here, that's where Chebysheff was from. The proportion of data points with a value more than k standard deviations away from the mean is at most 1 over k squared. And remember, so for instance, how many data points can we have where the value is more than, say, 2 standard deviations away from the mean? That's 1 over 2 squared, or 1/4, or 25%. We can have at most 25 data points that are 2 standard deviations away from the mean, that are 2 sigma events. Now, our empirical normal rule says that we expect to have maybe 5% of our data points that are 2 sigma events if we have a bell-shaped distribution. But Chebyshev, remember, applies to any distribution. The only assumption we made are finite mean and sigma, mean and standard deviation. So in the context of our chapter 4 notation with probability that we can bring to bear on this problem now, we can rephrase this. We can say that our claim is that the probability that the absolute value of xi minus mu is bigger than or equal to k sigma, that probability should be less than or equal to 1 over k squared. And absolute value of xi minus mu, that is the distance that a specific data point's value is away from the mean. So if I'm looking at the probability that that distance is bigger than or equal to k sigma, the complementary event is that that distance is less than k sigma. In other words, what we're saying here is that xi minus mu is less than k sigma and bigger than minus k sigma. Or in other words, that xi is bigger than mu minus k sigma and less than mu plus k sigma. So this is just another way of saying that the value is within k standard deviations of the mean, between mu minus k standard deviations and mu plus k standard deviations. So saying that the probability that the value is more than k standard deviations away from the mean is less than or equal to 1 over k squared is equivalent to saying that the probability that the value is less than k standard deviations away from the mean is bigger than 1 minus 1 over k squared. So we're using our rule of complementary events here, and then just a little bit of logic to realize that we need to flip that inequality sign. So what does the proof of this look like? We didn't prove it, we just stated it. So let's go through the proof. This is an important idea, Chebysheff's theorem. It basically says we can't have arbitrarily many data points that have value far away from the mean. So let's assume that our data points are listed in increasing order of value, so that x1 less than or equal to x2 and so on. We can then split our data points into 3 classes or 3 categories. x1 through xj are at least k standard deviations below mu. So for these ones, x1 through xj, x sub I is less than mu minus k sigma. For the ones in the middle, xj plus 1 to xj plus m minus 1. These little subscripts aren't super important what exactly they are, but I'm just being careful here to make sure that we technically include all of our data points. These are the ones that are within k standard deviations of the mean. And then these other ones here, xj plus m to xn, are at least k standard deviations above the mean. So if we think that we have a number line here, we have mu, we have a distance k standard deviations on both sides. So we have mu minus k sigma and mu plus k sigma. What we're saying here graphically is we're splitting this into three regions. One region that is more than k standard deviations below the mean, this region to the left of mu minus k sigma. One region that is within k standard deviations of the mean, it's between mu minus k sigma and mu plus k sigma. And a third region that is more than k standard deviations above the mean, that's where the value is above mu plus k sigma. So these are x1 through xj, xj plus m through xn, and whatever this one is, xj plus 1 through xj plus m minus 1. So those are our three classes. The middle class are the ones within k standard deviations from the mean, and the left and right classes correspond to these beginning and ending data points. Okay, so let's look at the definition of sigma squared. The definition of sigma squared is the mean squared deviation from the mean of the squared deviations from the mean. Or I take my sum of squared deviations from the mean, divide by n. But if I look at this, adding up n things, all of which are non-negative. If I take something and square it, the least it can be is 0. And if xi is not equal to mu, then it's strictly positive. If I get rid of some of these terms that I'm adding up, if I just, erase them, then the sum becomes, it either stays the same if all those terms that I erased are 0, or it gets smaller. So I can make the sum smaller by choosing to sum over not all of the data points. If I just pick certain data points to evaluate and then sum over, then my sum gets smaller. Here I'm picking just the data points where absolute xi minus mu is bigger than or equal to k sigma. In other words, I'm just using these data points on the edges and not these ones in the middle. However, I noticed that xi minus mu squared, well, xi minus mu squared is the same as absolute value of xi minus mu squared. But if I look at these two classes here, absolute value of xi minus mu is the distance away from the mean. For all of these data points that I'm interested in, the distance away from the mean is at least k sigma. The distance is at least k sigma away from the mean. And if I square both sides, I see that xi minus mu squared for each of these data points that I'm interested in, that I'm choosing to sum over, has to be bigger than or equal to k sigma squared. So if I were to replace xi minus mu squared with k sigma squared for each of these data points, specifically the ones that I'm interested in on the edges here, the left and right classes, well, then my sum only gets smaller because each of the terms can only get smaller. So I can make the sum smaller still by replacing xi minus mu squared with k sigma squared. But here, what do I have? I have 1 over n, and then I'm just adding k sigma squared. That's just a constant. I'm adding it to itself a certain number of times. How many times am I adding it to itself? Well, the number of data points that are in this left class plus the number that are in the right class. So I have 1 over n times k sigma squared, which I'm breaking apart as k squared sigma squared, times the number of data points with a value more than k standard deviations from mu. If I look at the number of data points that satisfy a certain criterion divided by n, divided by the total number of data points, that's just my empirical probability. That's just the probability that a randomly chosen data point has a value that's more than k standard deviations from mu. So these two bits, this number of data points over n, turns into this probability statement here. And then this k squared sigma squared is just some vestigial stuff. So what do we have if we zoom back out? We have that sigma squared is bigger than or equal to, note that all of these inequalities point the same direction, very important. Sigma squared is bigger than or equal to all of this stuff here. So that's what I've summarized here. But here I know that sigma squared is positive. I suppose if we had if we really, really wanted to be careful, we'd set up a special case where we say, okay, if all of the xi's have exactly the same value, then some weird edge case things happen. But if we assume that we're working with a data set where we don't just have the same value repeated a whole bunch of times and nothing else, that would be kind of a strange data set to really be super interested in analyzing. But we can divide through by sigma squared. Of course, if sigma squared is 0, this is true, right? But we can divide through by sigma squared here. And these go away. And then we can divide through by k squared. And we get that the probability that a given data point has a value more than k standard deviations away from the mean, that's what this says, is less than or equal to 1 over k squared. And that is exactly what Chebysheff says. So we have proven Chebysheff's theorem. And again, this idea of probabilities, I think, makes this a little cleaner. It makes it a little easier to understand after we got to chapter 4, rather than trying to talk about proportions and all that in chapter 3. I suppose we probably could have done it with the material in chapter 3, but I think it's just a little easier to go this route. The other important thing that we introduced is the law of large numbers. Again, we mentioned the law of large numbers, but we didn't prove it. And we're going to go through somewhat of a proof now. This is going to be in a couple of stages. So there's a bit of a process to proving this, and we're not going to, there are several laws of large numbers. We're going to prove a certain law of large numbers. And maybe at first it'll kind of look like we really didn't prove much of interest at all, but we'll actually see that we proved maybe a little more than we think we did. Remember that the law of large numbers, roughly what it said when we were in chapter 4, roughly what it said was that the empirical distribution that you get from a sample, the empirical relative frequency distribution, will look more or less like the classical probability distribution. If I took the whole population, if I set up some bins, some classes, and I looked at the probability of that class occurring, the probability of that outcome or event or whatever you want to call it, and then I compared that to, say, if I took a big representative, well-done sample from that population, and I split that sample into the same bins, the same classes, and I looked at the relative frequencies from that sample, the percentage of the data points that fall within that class, those two proportions for those different classes should match up pretty well. That's what the law of large numbers says. The empirical frequency distribution looks like the underlying frequency distribution. So let's try to prove this. We're going to start by proving what is sometimes called the weak law of large numbers. It's weak in the sense of the type of convergence. And we'll talk a little bit more about that later on. This is starting to touch into some areas that are a little beyond the scope of this course. So we're kind of straddling the line between stuff that really belongs in this course and stuff that's maybe a little bit more advanced. But just to give you a little bit of a taste of some of that additional material as well, and to show you what these kind of proofs, what this underlying discussion really looks like. So there's a lot of stuff in stats that is kind of subject to debate, that's very subjective. I think that this histogram looks better than that one or something. That's a very subjective thing. I think that this say measure of center does a better job of communicating what's important about this data than this one does. That's fairly subjective. But something like this, like proving the law of large numbers, this is completely objective. This just follows axiomatic rules and logic. So let's assume that we have x1, x2, etc., that these are data points in our sample. We're also going to consider, and this touches on an idea that comes up later in chapter 7, we're going to think about the idea of taking a sample. So I have a population over here, and maybe I want a sample of size 5. I probably want a bigger sample than that, but I'm just going to say 5 so it's easy to draw. So I take my sample of size 5 and I get my data set. From that data set, I can do things like compute X bar and so on, right? So I could take this and I could compute X bar, say, for this data set. But something that I realize is that actually this is already kind of a probability experiment, isn't it? It's kind of a chapter 4 type setup. There were a lot of other people or data points or whatever in the population that I could have chosen that I didn't happen to choose in this specific random sampling. If I told somebody else to go out and take a sample of size 5 of this same population, that person would probably get 5 different data points for their data set. They would get a different X bar then, probably. So this idea of which data point did I select first from the population, that's actually a random variable. That's a little bit like rolling a die or drawing a ticket out of a lottery. I reached into my population and kind of at random grabbed, one person or one data point or whatever from that population as my X1 for my sample. That's a probability experiment. If I say that each person in my population is equally likely, that's just like rolling a die or picking a ticket out of a lottery or something like that. So I could think of X1 as being a random variable. Again, if I reached back into that population and drew a different sample of size 5, I'd probably get a different X1. Also, X2 is a random variable, as is 3, 4, 5. Therefore, X bar is also a random variable. Okay, so we're going to think of these Xi's as random variables, and specifically, we're going to think of them as being independent, so that if I draw X1 and I see what number that is, that doesn't give me any information about what X2 or X3 or X4 are likely to be. So kind of in specific here, we're kind of drawing X1, pulling X1 from the population, writing down its value and putting it back. We're roughly thinking of this as being with replacement, or maybe practically speaking, maybe we're thinking that our population is large enough that even if we're not drawing with replacement, it's not a big deal. If we had a population of size 10 and we were drawing 5 people for our sample, that's not a very big population relative to the size of our sample. We would be worried about not drawing with replacement, that might cause some statistical anomalies. But if we had a population of 1 million, Are we really worried about drawing the same person twice in 5 draws? Probably not. So we're either thinking that we're drawing with replacement or that our population is many, many, many times larger than the sample that we're drawing. So we're not super worried about the with or without replacement difference. So that's what we mean by independent and identically distributed. And we're using the same population for each of the draws for our sample. So they should all be identically distributed. It should be distributed according to the same underlying population, right? I'm not measuring people's heights and, my population for X1 is a bunch of preschool kids and my population for X2 is a bunch of NBA players. And right, we have the same population, maybe all people in Pittsburgh or something that we're working with. So the distribution is identical between the first data point drawn and the second and third and so on. We're also assuming finite mean and variance. And we want to show the following. We want to show that no matter what positive number I pick for all epsilon bigger than 0, no matter how small this positive number is that I pick, the probability that my sample mean, which I'll call x bar sub n, the x bar computed based on a sample of size n. So in this case, it would be x bar subscript 5, x bar 5. But we're saying that what's the distance between x bar n and mu, the actual population mean? Remember, the reason that we're taking a sample is because we want to know something about the population, but we don't have the resources to access the whole population. So we're taking a sample and maybe computing x bar and hoping that that's a good estimate of mu. What the weak law of large numbers says is that as my sample size gets larger and larger, my sample mean approaches mu, the true mean. As I take a larger and larger sample, my sample mean computed on that bigger and bigger data set gets closer and closer to the actual population mean mu. So specifically what I want to show here is that no matter what positive number I choose, no matter how small it is, and no matter how small I choose this number epsilon, the probability that the distance between the sample mean and the population mean, the probability that that distance is bigger than or equal to some small positive number goes to 0, as n goes to infinity. This might seem like an overly technical way to prove this, but we really kind of need these technical details to make everything work out right. So again, this is where we're getting a little bit outside the scope of this course, but some of you who have had some more advanced math might actually recognize some of this material, and it might tie into some things that you've seen before. If you haven't seen this stuff before, it's not something that you need to know for the homeworks or the exams, but I'm just giving you a little bit extra background material here. So now let's suppose that we have a random variable, x, and in particular, that random variable is our sample mean. Remember, each data point in our sample is kind of randomly drawn from the population. That randomness transfers through or passes through to the sample mean, which is computed based on those sample data points. So our sample mean is also a random variable. So we're going to consider x bar n to be our random variable. Our sample mean for a sample of size n, that's our random variable that we're thinking about. And again, this kind of leads into chapter 7. So we're seeing it once now. We'll see this idea again in chapter 7 when we start to build up to things like confidence intervals and hypothesis tests. But x bar n is a random variable. This sample mean on a sample of size n is itself a random variable. So it has its own mean. It also has its own variance or standard deviation. being a random variable. So we could talk about the mean of x bar n, or mu subscript x bar n. We could talk about the variance of x bar n, sigma squared subscript x bar n. What are these means and variances? Well, let's figure out what mu sub x bar n is. The expected value of x bar n, well, this is from section 5.1. What's x bar n? It's the sum of the xi's over n. And I want to compute the expected value of 1 over n times x1 plus x2 and so on plus xn. But we had seen earlier in section 5.1 that the expected value is a linear operator. The 1 over n, that's just a constant. That's not random. We just say we're taking a sample of size 20. So this is 1/20th. That can just pop out in front of the expected value. It can kind of factor out of the expected value. And then we have the expected value of the sum of some things, but that's the sum of the expected values. We saw that these expected value properties we saw last time, or was it last class or the class before? I think it was last class. So the expected value constants come out and it splits up sums. That's how we get to this piece here. But each of these expected values, what is the average draw for x1? Well, that's just mu, right? That's just, so the mean of a sample of size 1 from a population, I suppose you could think of it as, is just mu, the mean of the population, as is the mean for x2 and so on throughout xn. So this is just like mu plus mu plus mu n times, it's n times mu. Get rid of those couple of mu's over there. Okay. So this is just n times mu. This is mu plus mu and so on all the way out with a 1 over n in front. 1 over n times n mu equals mu. So in a sense, the average of our averages is the population mean. So that's good. That actually shows that x bar is an unbiased estimator of mu. That on average, when we compute x bar, if I compute it for this data set and then I take another random sample and compute it for that data set and then yet another random sample, compute x bar for that data set, if I average all of those different x bars together, I should get mu if I take a bunch of random samples, get a bunch of different x bars, and then take their average. So the average of the averages is the population mean. That, I think, makes sense. What about the variance? Well, the variance, remember, constants can come out of the variance. So we're looking at the variance of x bar n, similar to expected value. Constants can come out, but when they come out, they get squared. So that 1 over n inside the variance comes out as a 1 over n squared times the variance of x1 plus x2 and so on plus xn. By independence, the variance of the sum is the sum of the variances. If we do not have independence, this wouldn't hold. But by independence, we can say this. I think I have a note down here about this, so we're just going to hold off on that for a minute. But by independence, we can do this, and we'll show why we can do that a bit later. But then the variance of x1, that's really just the variance of the population, which is just sigma squared. Same with variance of x2 is sigma squared, and all the way out to variance of xn is sigma squared. I just have n lots of sigma squared that I'm adding together. And that's all multiplied by a 1 over n squared in front. 1 over n squared times n sigma squared. One of the factors of n cancels, but I get sigma squared over n. One of the factors of n is left in the bottom. Okay. So we have these relationships between the mean and standard deviation. Let me erase my scratch work here. And I'm just going to highlight the important bits. So written in more concise notation, we have this statement, but written out a little more explicitly, we have these statements here in the blue squares. Now let's come down to Chebysheff. Remember, Chebysheff says that the probability that a random variable that was like my xi minus mu is bigger than or equal to k standard deviations from the mean, it's bigger than or equal to k sigma, was less than or equal to 1 over k squared. So if instead of just having a random variable xi, if I made my random variable instead x bar n, the probability that x bar n minus mu in absolute value is bigger than or equal to k times the standard deviation of x bar n, the square root of the variance of x bar n, that's going to be less than or equal to 1 over k squared. So we're going to choose k such that k sigma squared equals epsilon. So if somebody gives us epsilon, we take epsilon, we divide it by sigma x bar squared, by sigma x bar. If somebody tells us what they want epsilon to be, remember epsilon was some small, typically we think of it as small, positive number. If somebody tells us what they want it to be, we take that number, divide by sigma x bar, no squared, and then that's what k we're going to use. So we're going to choose k this way. This says that 1 over k squared is sigma x bar squared over epsilon squared. But I know what sigma x bar squared is. I know what the variance of x bar is. That's just sigma squared over n. So this is sigma squared over n with an extra epsilon squared on the bottom. Now, what happens to this as n goes to infinity? Well, epsilon is fixed. Epsilon was the specific number that we picked at the beginning. We could pick it any way that we want. You could pick it a very small number, 10 to the minus 5 or something. But once you pick it, it's set in stone. Sigma squared, well, that doesn't change. That's just a characteristic of the population. That doesn't change as our sample size increases. Our sample doesn't affect the population variance at all. And then we have this n on the bottom. If we have a number in the bottom of a fraction that gets bigger and bigger and bigger, that fraction has to go to 0. So picking our k sigma squared this way, what have we shown? We've shown that, remember I keep saying k sigma squared. I should be saying k sigma. By picking my k sigma this way as epsilon, probability xn, x bar n minus mu in absolute values is bigger than or equal to epsilon. I pick this that way, is less than or equal to 1 over k squared. Remember, that's this thing, sigma squared over n epsilon squared. And this goes to 0 as n goes to infinity. That was exactly what we wanted to show. So just to recap, what have we shown in kind of more plain English, or as plain of English as we get in statistics? We've shown that as n goes to infinity, as our sample size gets larger and larger, the sample mean goes to the population mean. Now you might be looking at this and saying, wait, I thought you said this was the law of large numbers. Doesn't the law of large numbers say a lot more? Doesn't it say that the sample frequency distribution goes to the population frequency distribution, not just a statement about the means, but the distributions as a whole? And actually, we have essentially already proved that. By making the statement about the means, by proving the statement about the means, we've kind of proven the statement about the frequency distributions already. Let's look at why that is. So as I mentioned here, the law of large numbers in chapter 4 said the relative frequency distribution obtained from a sample of size n approaches the true probability distribution, the underlying probability distribution, as n gets larger. So we made the statement about the whole frequency distributions, not just the means. And the mean is what we proved above. Sometimes this is called the Erdos law of large numbers. There's several different laws of large numbers, but this is kind of more or less the one that we are looking at. So why is it sufficient to prove this for the mean in order to be able to conclude the statement for the distributions as a whole, for the total frequency distribution? Well, let's look at this. Let's consider an event E. And for each outcome in our sample, for each xi, regardless of how we define the event, either xi is in the event or it's not in the event. I think we can agree with that. And let's make a new random variable called yi. Yi is 0 if xi is not in the event, and it's 1 if xi is in the event. So I don't know, the x's might be, heights of people in Pittsburgh. We have 1 million people in Pittsburgh, let's say, and we're going to take a sample of size 10, and I'm setting up the event that a person is over 6 feet tall. So I take my first draw from the population, I get x1. X1 is, 6 feet 2 inches. So that's my x1. But I can look at a different variable that's related to that. I can ask, is that first person taller than 6 feet tall? Well, they were 6 feet 2 inches. So y1 would be 1. Y1 indicates that, yes, this person is above 6 feet tall. They are in the event. Maybe the second draw that I pick, x2, is like 5'8". Y2 then would be 0 because that 5'8" person is not in the event taller than 6 feet tall, and so on. So we could go down each of our xi's. We can look at a certain event and we can ask, is that xi in the event or not? If it is in the event, we give it a 1 for the yi. If it's not in the event, we give it a 0 for the yi. Then I can ask how many. So I now have a list, a data set of size n. I have a list of xi's, x1 through xn. I can ask how many xi's are in the event. How many of my data points satisfy the event that I'm interested in? How many fall into the bin that's represented by that event? Well, that's just the sum of the y's, right? Because each time I encounter an xi that is in the event, I encounter a 1 and I just add 1. And for all of the xi's that are not in the event, they're just 0. So I just add 0 to the tally. So as I'm going down, if I want to say how many xi's are in the event, I could count the actual xi's, or I could go down the column of yi's that are just indicators of being in the event. Just 1 if it's in the event, 0 if it's not, and I could just sum the column of yi's. So the sum of the yi's is the number of data points that are in the event. What is my sample probability of being in the event? What's the probability of being in the event based on my sample? What's my empirical probability of being in the event? Or what is my empirical frequency associated with that event? That's just the number of outcomes, the number of sample data points that are in the event divided by the total number of sample data points. That is just the sum of the yi's divided by n. But wait, the sum of the yi's divided by n is just y bar. It's just the mean of y. It's just the mean of y for a sample of size n. But wait, this, by the weak law of large numbers that says that means converge, sample mean converges to population mean, this says that the sample probability of an event must converge to the overall, the underlying probability of the event through the weak law of large numbers. So by making a statement about the mean, I can construct this kind of indicator random variable that just says, is my outcome in the event or not? And using the weak law of large numbers on this indicator random variable, I can connect the probability of an event under the sample with the underlying probability of an event. The probabilities approach one another as well. So we even get a little more than we had desired. It's not only that the relative frequency distribution converges, it's that any event that I'm interested in asking about in the sample side of things, the probability of that under the sample is going to converge to the underlying probability of that event in the population. Whether that probability is related to a single outcome, i.e. a frequency distribution kind of idea, or maybe a collection of outcomes or whatever. So probabilities converge to one, not converge to one another. The sample probability converges to the underlying population probability. And the real mechanism of making that happen is this convergence of means. So that's our weak law of large numbers. A couple of technical notes. These are the note C is, kind of at the edge of the discussions that are really the content for this course. And part D is just a little interesting tidbit that's beyond the scope of the course, but that you might find interesting. So one note on the variance of x bar n. I kind of cheated here a little bit. I just said, oh, by independence, this should work, but we never actually showed that. We're going to show that here. I'm not going to go through all of the details super carefully, because again, this is kind of at the border of what I would consider actual material for this course. It's certainly not something that's necessary for homework or exam or something, but to be thorough, I will give you kind of a sketch of why this is true, why the variance splits apart sums under the assumption of independence. Very important that that assumption of independence holds. We saw how probability splits apart products under independence, or probability of A and B is probability of A times probability of B. Under independence, we get something qualitatively similar for the variance. The variance of the sum is the sum of the variances. The variance in a sense splits apart sums, but under independence. Okay, so let's take a look at the variance of x plus y. We're just going to look at the variance of the sum of two random variables, because writing it out for x1 through xn all added together is just a huge mess. So we're just going to look at two random variables, x and y, add them together, take their variance. What do we get? We can write out what the definition of variance is. The variance of a random variable is the expected value. So the variance of, let's say, z is the expected value of z minus mu z squared. Or this is the expected value of, the notation gets a little messy here, but z minus expected value of z all squared. Or this is the expected value of z minus, well, this expected value of z, this is what's expected value of x plus y up above. And I want to switch this z also to x plus y. So I'm swapping in z equals x plus y here. And that's what I have here. Be a little careful. There's an outside parentheses here. The expected value splits apart the sum. So I can make this inside of the expected value. I can make it x minus the expected value of x, or x minus mu x, plus y minus mu y. That all gets squared. So I have the expected value of, a plus b all squared. I know that that's a squared plus b squared plus some other stuff. So that's the expected value of the first stuff squared, x minus mu x all squared, plus the expected value of the second stuff squared, y minus mu y all squared, plus some other stuff. So in particular, I get expected value of x minus mu x all squared. That is just the variance of x. That's what this term is. This term is the variance of y. And then I get some vestigial stuff. I get my cross terms from that, multiplying out that binomial, right? I get a 2ab kind of deal. I get a 2 expected value of x minus mu x times y minus mu y. And this is the stuff that I'm not sure what to do with, right? And in fact, the claim is that if x and y are independent, then this stuff at the end here is 0. And then the variance of x plus y equals variance of x plus variance of y. And this stuff is just 0. That's the claim. I feel like John Madden sometimes when I'm drawing on these things. I don't know if any of you are old enough to have seen the John Madden like memes when he was commentating on football and he's drawing all over the screen. But anyway, so the claim is that the expected value of x minus mu x times y minus mu y equals 0 if x and y are independent. Now, one thing, when we want to try to prove a claim, we want to look at what tools are available to us. I'm saying this is true if x and y are independent. I'm probably going to have to use independence somehow. And I have one really big tool for independence that it splits apart ands, right? Probability of A and B equals probability of A times probability of B under independence. So that's going to be an important tool to look for a place to use. If I multiply this out, this binomial here, I end up with expected value of x times y for my firsts. My outsides give me expected value of x times mu y. My inside gives me minus mu x, expected value of y. And then my lasts give me plus mu x mu y. But expected value of x is just mu x, and expected value of y is just mu y. So I have minus 2 mu x mu y plus 1 mu x mu y. I have expected value of xy minus mu x mu y minus expected value of x, expected value of y. This has very much that kind of feel of like expected value of x squared minus the mean squared. It has that similar feel to it that we recognize from the variance calculations in section 5.1. Okay, so what's expected value of x times y? If I can show that expected value of x times y equals mu x mu y, then their difference is 0. Therefore, this whole thing is 0, and I get exactly what I wanted. So I'm going to try to show that expected value of x times y equals mu x mu y. That's my kind of short-term goal right now. What's expected value of x times y? Well, the expected value of stuff, the expected value of, g of x is just g of x1 times probability of x1 plus g of x2 times probability of x2 and so on. Well, for two random variables, x and y, x has some different possible outcomes. Let's say x1 through, let me make sure I'm using my right. Yeah. So the random variable x has a sample space x1 through xn, and the random variable y has a sample space y1 through yn, or y1 through ym. There. So x and y have, x has outcomes x1 through xn, y has outcomes y1 through ym. We're assuming finite outcomes for each of these, discrete case, finite outcomes. So x has potential outcomes x1 through xn, y potential outcomes y1 through ym. So what are my possibilities for x times y, this product? Well, I could have, for instance, x1 times y1 or x2 times y1, or x3 times y1, all the way out to xn times y1. Those are all possible outcomes for this new random variable x times y. Or I could have x1 times y2, or x2 y2, or xn y2, all the way out through x1 ym, x2 ym, out through xn ym. These are the possible outcomes for the product x times y. These are all the possible assortments of x and y that can contribute to this product. So for instance, I have x1 times y1 is a possible value for this product x times y. And that occurs with probability. The probability that x equals x1, the random variable x equals x1, that we've ended up with that outcome from the list of x's, and y equals y1, that from the list of y's we end up with this outcome, y1. Same with, we have a different outcome for the product that could be x2 times y1. And that happens with probability x equals x2 and y equals y1, that I've picked x2 out of this list and y1 out of that list. There's some probability of those happening, sometimes referred to as the joint probability. Trying to undo these parentheses there. And so on. I've written it a little bit shorter. Instead of x equals x2 and y equals y1, I've just written x2 and y1, and so on. I do this for each of my possible pairings. There are n times m of those pairings, from 1, 1 down through n, m. But now I can use my big hammer here. I can use my big assumption of independence, because now I have a probability of A and B, probability of one event and another event both occurring. And remember, x and y are independent. So if I know that x equals x1, that doesn't tell me anything about the likelihood that y equals y1 or y equals y3 or anything else. Knowing what x is doesn't affect what y is likely to be, and vice versa. They are independent. So therefore, I can break the probability of event 1 and event 2 into the product of the probabilities of the events. So this uses independence, splitting all of these ands into timeses, roughly speaking. But now what I can do is I can say, out of this first row here, x1, y1, x2, y1 through xn, y1, every one of them has a y1, and every one of them has a probability y equals y1. I can factor that out. I get y1 times probability that y equals y1, factored out from that whole first row. And what's left in that first row is x1 probability x1 plus x2 probability x2, all the way out through plus xn probability of xn. I can do something similar in the second row, where I factor out a y2 times probability y equals y2, leaving behind the same bracket with the xn's, and all the way on down to the mth row, where I can factor out ym, probability of ym, leaving behind that same x bracket. But wait, what's x1 times probability of x1 plus x2 probability x2 plus xn probability xn? That's just the expected value of x. That's just mu x. That's what it is in the first row and the second row and all the way down, just all expected value of x's. But now every term, these are all added together. Every term has an expected value of x. But wait, I can just factor out expected value of x from everything now, leaving me with what? y1 probability of y1 plus y2 probability of y2, and so on. I actually think the algebra is pretty nice and elegant in this case. So once I factor out all of the expected value of X bits, I'm left with a string of stuff with Y's, but I recognize that this is exactly expected value of Y. So I used independence here. I leaned heavily on that so I could split all of these ands into products of two probabilities. And I absolutely needed that in order to start factoring stuff out. But as soon as I could factor stuff out, I could collect things and recognize expected values here and there. And I end up with the result that under independence, expected value of X times Y equals mu X mu Y, which means their difference is 0, which is this, which means that this stuff is 0, which means this stuff goes away if we have independence. So under independence, the variance of X plus Y equals variance of X plus variance of Y. Under independence, the variance splits sums apart. If we don't have independence, then we have this nasty term here that typically is very messy. This is one of the reasons that people really, really like to assume independence, maybe even in cases where it's questionable or just flat out not warranted, because it just makes things so much easier if you assume independence. So I think that tightens up the proof up here, where we kind of skipped that step because it was more of a technical detail and kind of broke the thrust of the proof up here. But that wraps up that technical detail, shows a little bit of work with expected value, you know, a little bit more advanced than the stuff we talked about, but sometimes practicing or being exposed to things that are a little more advanced makes the moderate level stuff a little more digestible. And then one last topic that's of kind of, you know, maybe a side interest. We called this the weak law of large numbers, but and at first you might have said, oh, maybe it's the weak law of large numbers because it only applies to the mean or something, but we really showed that it really applies to the whole distributions. So why is it the weak law of large numbers? Well, it's the weak law of large numbers because of the method of convergence. The strong law of large numbers says kind of the exact same thing. It says that the sample mean approaches the population mean as the sample size gets larger. But there's a little nuance in the type of convergence. So what we showed is convergence in distribution. So that there are several different types of convergence, or sorry, what we showed up above, what we showed for law of large numbers is convergence in probability. This is weaker than some stronger types of convergence. The central limit theorem that we'll talk about in chapter 6, our other big theorem in the course, uses this idea of convergence in distribution that's even weaker than the type of convergence we used in the weak law of large numbers. And as kind of an example, let's take a look at the idea of convergence. Let's say that we had a distribution that has value 0 that occurs 1 minus 1 over n proportion of the time, and value n that occurs proportion 1 over n of the time. So we have a probability distribution with two outcomes, 0 or n, where the probabilities are 1 over n for this guy and what's left over for 0. What's the expected value? What's the mean of this distribution? Well, it's 0 times 1 minus 1 over n, that's 0. And n times 1 over n is 1. If I add these together, I always get 1 for the expected value for the mean. So the mean of this distribution is always 1, no matter what n is. If I look at the limit as n goes to infinity, this first outcome, its probability goes to 1, and the second outcome, its probability goes to 0. So what does my distribution look like? As n gets bigger and bigger, the distribution on the left converges to a distribution like this, where I just get outcome 0 with probability 1. But what does the mean for n equals 1? It's 1. What does the mean for n equals 10? It's 1. What does the mean for n equals 1,000? It's 1. As n gets bigger, the mean is always 1. It does not converge to 0. Clearly, the mean here is 0, right? So just because the underlying frequency distributions converge does not mean that the means necessarily converge. Convergence in the mean is stronger than convergence in distribution. When we talk about the central limit theorem in chapter 6, that uses a type of convergence that's convergence of distribution. So it's a fairly weak type of convergence. And there are some, strange paradoxes and things that go along with that. Again, a little beyond the scope of this course, but, for some of you that have exposure to, some other math courses or topics, you might find this somewhat interesting that, usually in say pre-calculus or something, there's just kind of like one kind of limit or one kind of convergence, and probability there are several different kinds, and which kind you're using kind of dictates what conclusions you can make on the basis of, say, a certain theorem. Okay, so that wrapped up some of the theoretical background for Chebysheff, for weak law of large numbers, and a little more exercise on things like expected values and variances and all of that. And then we're going to move into what I think of as kind of the last part of chapters 4 and 5, Bayes' theorem. The book introduces this in chapter 4. I don't think that's exactly the right place to introduce it. But with Bayes' theorem introduces well, let me say this. There are a couple ways to look at Bayes' theorem. On one hand, you could look at it as just kind of another tool in the toolbox that you can use in this context of probability and maybe something like chapter 4. But I think that's a fairly limiting way of looking at Bayes' theorem. We're going to take a little more well-rounded look at Bayes' theorem, and we're going to see how it can really be used to what I think is a more full potential than maybe the treatment that the book gives it. Okay, so let's take a look at a motivating example. Suppose we have two car manufacturing plants, plant 1 and plant 2, which I'll just abbreviate as P1 and P2. And that each produces the same two types of cars, type 1 and type 2. And again, I'll just call them T1 and T2. And suppose that of the cars produced by plant 1, 10% are type 1, 90% are type 2. And of the cars produced by plant 2, 95% are type 1 and 5% are type 2. And then suppose that these two plants produce the cars, they get kind of mixed together at a warehouse. They get shipped out to a car lot from the warehouse. We go to the car lot and we observe a car of type 1 on the lot. We see that, okay, this is, whatever, Ford Mustang or something on the Ford lot. And we would like to infer then, what's the probability that it came from plant 1 rather than plant 2? In other words, we would like to estimate the conditional probability that the car came from plant 1, given that it's of type 1. So I know that, for instance, plant 1 has, that they make, what I say, like 10% of the cars they make are Mustangs and 90% are, I don't know, Explorers or something. And plant 2, 95% of the cars they make are Mustangs and 5% are Explorers. Given that I walk onto a car lot and see that a car is a Mustang, what's the probability that it came from plant 1? And we'd like to estimate this, and we might look at this and say, well, and what a lot of people would do is they look at this and say, well, plant 1 doesn't make a large proportion of Mustangs, plant 2 makes a large proportion of Mustangs. So obviously this probability is low. There was an economist, maybe psychologist, Grether, who did experiments with these kind of things where he would ask people kind of similar types of questions and ask them, what's the probability? Is it low, moderate, or high? And, in a situation like this, most people would say, I think the probability is pretty low. But really, there's another option. Are we missing an important piece of information? Is this kind of an intractable question? Do we need more information? And the answer is actually yes, we need more information. Let's suppose there are a total of 200 cars that were made. How many of them came from each plant? For instance, if plant 2 was shut down for the last 3 years for whatever reason, for retooling or something, hopefully it wouldn't take them that long to retool, but let's just suppose. Well, now what's your estimate for the probability that it came from plant 1? Like basically 100%, right? So it's very important to know what the initial proportion of cars coming from plant 1 versus plant 2 are. Maybe plant 2 is a much smaller plant and plant 1 is a much bigger plant. Maybe plant 1 is just cranking out tons and tons and tons of cars and plant 2 not so many, or vice versa. Or maybe they're pretty balanced. So let's suppose that plant 1 produces 90% of cars overall and plant 2 10% of cars overall. Well, what does that mean? That means that 180 cars came from plant 1. So the initial 200 cars, 180 or 90% of them came from plant 1, and 20 came from plant 2. Coming out of plant 1, we have type 1 cars and type 2 cars. And same coming out of plant 2. Plant 1 makes 10% of the cars they make are type 1. So 10% of 180 is 18. And the rest was at 162, I think, of the cars coming from plant 1 would be type 2. Plant 2 made only 20 cars in the same time period that it took plant 1 to make 180. 5% of their cars are type 2, so 5% of 20 is 1 is type 2, and 19 are type 1. So what is probability of plant 1 given type 1? Well, I can look at all of the ways to get a type 1 car and ask what proportion of those came from plant 1. Or I can say this is probability of plant 1 and type 1 over probability of type 1. This was just our formula for conditional probability. Plant 1 and type 1 is 18. And I mean, this would be, 18 over 200 or whatever, but we're going to have a 200 on the top and the bottom, so we can just count the numbers. The denominators will divide out. What's the overall probability of getting a type 1 car? 18 plus 19. We can see this is pretty close to 50%. It's 18 over 37. Or let's see what that is. I'll just do it real quick on my phone. So we don't have to bring up the calculator. So about 48.6%. So a fairly moderate probability. The fact that plant 1 produces way more cars in general than plant 2 offsets the fact that the proportion of type 1 cars that plant 1 produces is relatively small. So plant 1 produces a lot of cars overall, a small fraction of which are type 1 cars. Plant 2 produces a small number of cars overall, a large fraction of which are type 1 cars. So those two kind of balance. And this can be very tricky in practice when people are estimating probabilities. We talked about subjective probability not being a great method of estimating probabilities because, a lot of times there are hidden variables like this that we just don't take into account. There are a lot of examples of this. And this is one of the reasons that, that Bayesian statistics are so adamant their camp is right. Because Bayesian statistics really thinks about these ideas, these what we call prior probabilities. Frequentist statistics kind of sometimes leaves them by the wayside a little bit in some situations. Okay, so Bayes' theorem. This is what Bayes' theorem says. It's really a pretty straightforward proof. It's noting that we can write probability of A and B in two different ways. Probability of A and B, where A and B are dependent events. We can write it as probability of A times probability of B given A. Or we can write it as probability of B times probability of A given B. Since A and B are, since the and operator is commutative, A and B is the same as B and A. So I can just exchange the roles of A and B and get an equally valid statement. But that means that these two are equal to one another. Let me zoom in here a little bit, just in case it's a little hard for you to read. These two are equal to one another. And then we can just divide by probability of B. We get probability of A given B equals probability of B given A times probability of A over probability of B. We could go through the same calculation up here that we did with tree diagrams and conditional probability. We could use Bayes' theorem for maybe a cleaner approach, maybe a less involved approach. What's the probability of plant 1 given type 1? Well, I don't know that directly. That's not one of the pieces of information that I was given. I'll apply Bayes' theorem. What Bayes' theorem, in a sense, lets me do is flip this conditional around. Instead of plant 1 given type 1, instead of conditioning on the type of car, I can choose to instead condition on which plant. I can switch this to probability of type 1 given plant 1. But importantly, I need to multiply and divide by probability of plant 1 over probability of type 1. Now, what's the probability of type 1 of a type 1 car given plant 1? That's 10%. That's a piece of information that I just have ready access to. What's the overall probability of plant 1? If I just pick a random car, not of a specific type, what's the probability it came from plant 1? That I also have good access to, 90%. What's the overall probability of type 1 of getting a type 1 car? This can happen in two ways. I can get a car that's a type 1 car and came from plant 1. Or I can get a car that's a type 1 car and came from plant 2. And those would break up this way just using my basic probability of A and B formula. So my probability of type 1 car given plant 1 is 10%. I'm just leaving all the percents off here. I'll just think of the percent as kind of a unit. I'm just leaving it off. I see this same term that's in the numerator is the first term in the denominator, so I get a 10 there as well. Given that a car came from plant 2, what's the probability that it's a type 1 car? 95%. And then what's the overall probability of plant 1? If I didn't sort them based on car type, if I just looked at a random car in the car lot, what's the probability of that car is from plant 1? 90% here as well. And a random car in the car lot, what's the probability is from plant 2? 10%. We see that the 10s actually all divide out, and I get 90 over 90 plus 95. I can divide out a factor of 5 from there. And that gives me 18 over 18 plus 19 once I do all of that simplification, which is exactly what we got up here for somewhere in the ballpark of 49%, a moderate probability. So you might ask yourself, okay, I mean, it's maybe a nice little trick. It can maybe save a couple lines or save drawing a picture or something. It's, why am I making such a big deal about this theorem? Why did I specifically want to wait till after chapter 5? Well, there's two ways that we can think about this. There's the very frequentist way. I've kind of hinted at a couple of times that there are different philosophical interpretations of probability. And this is the frequentist approach. This is the approach that would be consistent with most of what we're covering in this course, including things like confidence intervals and hypothesis tests later on, where we say, okay, it's a pretty nice little tool. It lets me flip the condition around. I can change probability of A given B. If that's an inconvenient probability to try to compute based on the information that I have, I can turn it into probability of B given A, which is not the same thing. Be very careful. These two conditionals are not the same. I can flip the condition. I can find probability of B given A instead, provided that I multiply by this ratio, probability of A over probability of B. So it's a little tool that lets me change which event I'm computing the probability of and which one I'm conditioning on. I can flip the condition, so to speak, across that given line, and I can compute probability of B given A instead of probability of A given B. Maybe that's a little easier for me to compute in some situations. Okay, I mean, that's pretty nice. What's the big deal? And I mean, this little picture here kind of goes along with that. But really what the big deal is that a Bayesian statistician, I think it's a little funny to call people Bayesian statisticians or frequentist statisticians, but somebody approaching this with the perspective of the Bayesian philosophy would ask, okay, what is probability? Well, the frequentist idea of probability is if I repeated this probability experiment over and over, lots and lots of times, say 1,000 times, sometimes the event would happen, sometimes it wouldn't. What proportion of times on repeated experimenting would the event happen? That's what I mean by probability. For things like rolling dice or spinning roulette wheels or something, that is a very sensible thing to ask, because we can roll a die 1,000 times and see what happens. And maybe we are interested in what happens on 1,000 rolls of the dice, right? Or maybe we are interested in what happens on 100 decisions that we make regarding our investment portfolio over a lifetime or something like that. But what if I only get one chance? What if it's like, okay, you have, a medical condition, you need to decide on a treatment. You got to decide treatment 1 or treatment 2, you don't get to do that 10,000 times. So what's another way to think about probability? Another way of thinking of probability might be to think of, say, worldview or and the word just escaped my mind, degree of belief. So we could think of probability as representing something along the lines of degree of belief, something very individual and maybe subjective. It's, if I say this has an 80% chance of working and this has a 20% chance of working, this other thing has a 20% chance of working, I'll probably go with the 80% one because I believe that is going to work better for me. I can't, experiment 10,000 times and see how it works, or I can't average over 10,000 individual probability experiments like I could with, say, an investment portfolio, where if I make a few bad decisions, but mostly good decisions, I get to kind of average over those. I only get one chance and one outcome. So the Bayesian would say, well, this idea of probability represents a worldview. So maybe probability of A, the probability that I think it's going to snow tomorrow represents a certain worldview. Maybe I think it's probably not going to snow tomorrow because I look outside and it looks sunny, right? Maybe I say, okay, I think it's not going to snow tomorrow then. But then all of a sudden, like, the sky turns gray and I look at the forecast and the forecast says, oh, there's a big snowstorm moving in. I have an update to my worldview. I have more information that has entered the picture that I didn't have before. Now, I don't want to just jump ship and just go with the new information. I mean, I had presumably a reason that I had the first worldview. So I don't want to abandon that altogether. but I also don't want to dig in my heels and ignore any new information, even though this is what our psychology tends to make us whatever want to do. I don't want to dig in my heels and just abandon any new information and just, put on the blinders and stick to my worldview. I want a systematic way to incorporate newly acquired information into my worldview that also respects the current worldview that's presumably been obtained by an accumulation of previous information. So the kind of joke goes something like, if somebody flips a coin, if somebody bets you $1 or something that they can flip 10 heads in a row on a coin, and they flip a coin and they get 10 heads in a row, do you think the person cheated? And it's like, well, if it's your 4-year-old niece, probably not. If it's the, slicked back hair guy in the bar, probably yes. The frequentist would say, oh, well, they're the same thing. The Bayesian would say, well, I mean, the slicked back hair guy in the bar, I've had lots of experiences with types of folks like that, and they have, cheated me in the past. And my 4-year-old niece, I don't think she's really cheated me before. So right, we would look at surrounding information and in our worldview, and not just the probability of the event happening. Now, if our 4-year-old niece was able to flip 100 heads in a row, then I might start thinking she's cheating, right? Then kind of the updated evidence becomes overwhelming relative to the previous worldview. So we don't want to just abandon our worldview willy-nilly and when new evidence comes along, because then we're just bouncing all over the place like a ping pong ball. But we also don't want to ignore new information, because that seems non-scientific or that seems like folly. So we want to incorporate the new information in a systematic way. That's the Bayesian perspective. How do we do that? Well, I consider that I had a worldview. I had some degree of belief in event A happening. I obtained some new information, specifically the knowledge that event B has occurred. I want to update my probability of event A. I want to update my degree of belief in A in light of the new information. This new information might make me think that A is more likely to occur. It might strengthen my belief in A's occurrence, or it might weaken my belief in A's occurrence. So 2 ways from the car perspective, 2 ways of kind of visualizing this. We can just say, okay, well, this conditional was that we wanted to find was stated in a way that's kind of annoying to find directly from the information I had. Wouldn't it be nice if I could just flip it around? And then all of the pieces that I need are just readily available for my problem. It's just a tool in the toolbox that was helpful here. The second point of view is this: if I walked onto a car lot and for whatever reason they had all the cars covered up and I couldn't see what make or model or color or anything they were, and somebody pointed to a car and said, that car there, which plant do you think it came from, plant 1 or plant 2? I'd say 90% certain that it came from plant 1. And then they pull the cover off and I see that it's a Mustang, and I see that it's a type 1 car. And then they say, okay, well, now that you've got some more information, what's your updated degree of belief, your updated probability that it's from plant 1? Now that you know that it's type 1, I got some more information that it's a type 1 car, and I know that's a little less consistent with being plant 1, a little more consistent with being plant 2. So my probability goes down from 90% to 49% on the basis of the new piece of information I have. And I could even take this further. Maybe I know that plant 1 produces cars of this or that color at a certain rate, and plant 2 at a different rate, and I can observe what color that Mustang is, and maybe that helps me narrow down a little more, right? Or another example could be, I look at a patient and they have a certain sign or symptom, and I say, okay, I have a differential. I have 6 disease processes that might lead to such a sign or symptom. Okay, I mean, I have some background knowledge. If I have been a doctor, a PA, or a nurse for 10 years, I say, okay, this is probably a more likely disease. This is probably less likely, and so on. So let's run a test. We get a test result back. We don't just want to jump ship on 5 of the disease process and the diagnostics because of the result of one test, but certainly that test is going to inform things. It's going to shake up that list a little bit. Maybe it makes the thing I had in third place pop up to first place now, and first place go down to second place. And right, I got a little more information. I revise my differential. Maybe then I run another test, or I investigate, does the patient have these other signs or symptoms or something? And right, I get new piece of information here and there. And after I get several new pieces of information, maybe I can narrow it down to where all of a sudden one disease process is very likely, 95%, and the rest of them are fairly unlikely, 1 or 2% or something each. But that's after incorporating, several pieces of information and going through this process over and over again. Now, of course, your PCP is not going to sit there and do a Bayesian calculation on every question they ask you. They're going to use their clinical experience and their medical knowledge to maybe do that a little more implicitly. But sometimes, if you go for genetic counseling for, say, pregnancy screening kind of thing or something, they might actually sit down and, probably not in front of you, probably behind the scenes before they meet with you, but they might actually sit down and actually do the calculation and, work out what the likelihoods are. So again, there's two paradigms, two paradigmata, frequentist versus Bayesian, two different ways of thinking about this. It's the same mathematics, but a different thought process. Okay, I just realized that I can talk about this stuff forever. So when we come back, we will move on to a couple other examples in this topic in the Bayesian perspective using Bayes' theorem. And I think we'll really see the power of Bayes' theorem in the Bayesian perspective. Very important that that's not to say that the frequentist perspective is junk or whatever. They're two different perspectives that are, I think, good for two different use cases. All right,